Okay, got some vocabulary words for you today. Now, last time we saw this thing called p-value, and let's reestablish our neural pathways to that information. Try to explain in full detail as best you can, what does it mean to say something like this? P-value less than 0.05. What does that mean? Okay. Of course, it's always best if you put it in your own words. You don't want to just copy definitions or parrot memorized phrases or anything like that. You want to, kind of think it through yourself every single time. It makes your memory stronger. But anyway, p-value less than 0.05. I might say something like this. It's less than a 5% chance, right? It's less than a 5% chance that such an extreme result. Remember, when we're talking p-values, we're usually talking about something that was unexpectedly high or unexpectedly low, or it could be just unexpectedly different. But anyway, it's less than a 5% chance that such an extreme result could be dumb luck. Could happen by dumb luck. Let's put it that way. Could have happened. How about if we put it that way? Could have happened by dumb luck. The probability associated with values that extreme, and we mean all the values that are that extreme, totals less than 0.05. It's less than a 5% chance that this is dumb luck. In other words, we're wondering if it really is dumb luck. Is it? Maybe it is. I suppose it could be. 5% chance. Such things happen. Lightning strikes. But it makes you wonder. That's the thing. It makes you wonder. So that's kind of a nice working definition of it. And let's just throw an example down there to make it maybe a little more clear. So Biff says, hey, he can pick the ace of hearts out of a well-shuffled deck. You shuffle it and you spread the cards out in front of him like a fan, and he'll be able to pick it out. Pick the ace of hearts from a well-shuffled deck. And wouldn't you know, he does it. And you're like, I wonder what the probability is that he could have done it. Well, you can calculate it because there's 52 cards, right? So it was a 1 in 52 chance that he would have picked the right one just by guessing, completely guessing. If you make that into a decimal, that's actually 0.019231. So guess what? I'm going to say, so yeah, the p-value of that is less than 0.05. So it's like, what's going on here? Of course, if you did that in front of me, I'd say, well, could you do it again? And let's say he does it twice. Twice in a row. Picks out the ace of hearts. I mean, you shuffled and everything. You tried to hide it. But if he does it twice in a row, now you might get more impressed, right? Because what's the probability that would happen? Well, he'd have to do it once, which is a 1 in 52 chance. And do it again, which is a multiplication, remember, multiplication rule. So that's a 1 in 2704 chance, which as a decimal is 0.000370 approximately. So now we're in the p less than 0.001 territory. Wow. So you're starting to get impressed and you're starting to doubt, is this really dumb luck? Boy, I'm not so sure anymore, right? Maybe this guy's got a trick. There must got to be a trick to it, right? That's what magicians do. They make tricks. So anyway, that was kind of like last lecture, right? So I got some new words for you today, new vocabulary words. And it's going to at first look like I'm kind of doing the same thing, but bear with me. So let's say we've got a graph of a little probability distribution. So it might be flipping coins or rolling dice or whatever. And so X is the number of successes you get. Remember, that was Bernoulli trial lingo. You're flipping 100 coins, successes ahead. How many heads do you get is like saying, how many successes did you get? And then this is the probability on the y-axis. And if it's an unfair coin or something, you might have it average out or peak at about 20, and it'll be almost look kind of like a bell curve. It's not a bell curve. It's a binomial distribution, but it looks awfully similar. Let's put it that way. And let's say it looks something like that. Now, these results over here, let's say that's a 5, getting 5 successes, whatever these are, coins, dice, whatever. So 0 to 5, that's a 0. 0 to 5, that region in there totals less than a 5% chance, right? Those would be, what would you want to call that? Well, they'd have a p-value less than 0.05. That's what you say. Or maybe on the high side, like maybe this is, I don't know, 35 or something. And maybe it ends at 60. I don't know. I'm just making things up. So it might be that results up here, if you totaled up all the probabilities of all of these results, getting 35 or 36 or 37 or 38 all the way up to 60, the total from 35 to 60 would total a probability less than 0.05. And so you say, whoa, those are high values, unexpectedly high with a p-value of 0.05. Okay, and of course the 20 is what we would call the mean, which has that symbol mu, and I think I'll use a different color for this. This would be the mean. You expected 20 on these for some reason. So what I want to do now is say, okay, fine, let's look at in the middle here. So what's going on here, since we put a p-value of 0.05 at this high extreme, and we put p-value of 0.05 at this less extreme, what does that leave? That leaves 90% of the results, right? There's 5%, there's 5%, here's the rest of them. 90% of the results are in the middle. And we have a word for that. Middle. Okay. So, word number one. We are, and here's the phrase, 90% confident. That's our new word. 90% confident that the next value, do this thing one more time, whatever it is, that the next value will come up between, what would that be, 5 and 35. Okay, so last time we talked about p-values. Hey, there's a p, if it's up here high enough, it's a p-value less than 0.05. If it's over here low enough, it's a p-value less than 0.05. Okay, well, in the middle then, that's 90%. And we say we're 90% confident that that's where the next result will be. It'll be in the middle somewhere, okay? That's confidence. And then here's another word for you. Ready? Results less than 5. Let's say 5 or less. Or 35 or more. The results at the extreme, so to speak, are called statistically significant. Statistically, let's try to get that phrase all on the same line here. Statistically significant. So that's our other big phrase for today, which is pretty much like saying the same thing as, hey, low p-value. But here's the thing, and maybe I'll get another color out, okay? When we say they are statistically significant, what does significant mean? It's a, S-I-G-N is kind of the root there, right? It's sign. It's a sign of something. It's a sign of what? So I'm going to say signaling. Get it? Significant. It's signaling. Is that 2 L's? Maybe. Signaling the possibility. It's like, hey, that result's weird. So it's signalizing the possibility that something other than just dumb luck might be at work here. Other than just dumb luck might be at work here. Maybe you check the deck and you say, oh, they're all aces of hearts. No wonder you're able to do this. It might be something like that. That would not be dumb luck. So other than just dumb luck might be at work. Might. You have to say might, of course. So it signals that, hey, something's suspicious here. Maybe this guy really is psychic and he can do this kinds of things. Or maybe there really is. Maybe this pill really does work. It really does reduce the number of headaches or whatever. Right? So statistically significant is kind of like another way of saying low p-value. And in the middle, we say we're confident we're going to get one of those results in the middle. Okay? So let me flip back up. Hence the name of our lesson, confidence and significance. So I've defined what they mean. Actually, I need to, I guess, work a little bit more on these definitions. And then we'll get to some examples. So when we talk about confidence intervals, and did you notice I just snuck a new word in you, Anya? Intervals. Confidence intervals, this just means the interval where you're confident, I guess. So confidence intervals are usually two-tailed things. And so what I mean, well, I'm going to draw this picture again. So here's our probability of distribution. So you're rolling dice, flipping coins, you're polling voters, whatever you're doing. So X successes or whatever, X occurrences, X results or whatever. The result X goes on this axis. The probability of getting that result goes on this axis. If it's a binomial or something, you might, or if it's a bell curve, in fact, you might expect something like this. Now, this is what 95% confidence level means, because 95% is very common. Very common. With like QC technicians will use a 95% confidence level. A lot of newspaper stories and stuff use a 95% confidence level. And so what does that mean? It means that 95% is in the middle. One of these data points in the middle. All of the, the chance of getting any one of these particular points adds up to 95%. Notice that only leaves 5% for both wings total. So there's a probability less than, you'd have to put half of it over here, 2.5%. So probably less than 0.025 of getting one of these results over here. And this would be a probability less than 0.025 of getting results over here. And now I want to emphasize something here. I'll say P.S. It is not that each of these results, the results on the end here, has a probability less than 0.025. But all of the results, so the probability of this point or this point or this point, this or that, etc. All of those points has a total probability less than 0.025. Okay, and same thing over here. This. They all add up to less than 0.025. And then all of these things that can happen in here, the total probability of this one, or this one, or this one, or this one, you add them all up, it'll add up to just about 95% in the middle. Okay, so you might notice right away that using a 95% confidence level, CL for confidence level, is the same as using a 0.05, we call it a significance level. Boy, am I throwing the words around today, right? Well, let's just refer to page 1. We were confident about the stuff in the middle, and if it was out here, we said it was significant, right? We're confident about the stuff in the middle, that we're going to get a result in the middle, I should say. And if it's on the end, it's statistically significant. So if we use a confidence level of 95%, it means there's 95% of the data is in the middle here. And if we use a 0.05 significance level, it means we're looking for 5% total on either wing. Total. 2.5% on each wing. Okay. And by the way, it is the convention. Usually we use percent when we're talking about confidence levels. And usually we use a decimal, and I'm not sure why this is, but we usually use a decimal for significance level. And why that is, I'm not sure, but that is the convention. You should follow that convention. Okay. So now that you hopefully are starting to absorb these words, these phrases, significance level, confidence, significance, p-value, all these words, I'm going to throw at you something that we've actually seen before, but now I'm going to give it its official name, the 2 sigma rule of thumb. So we've seen this already. So it just comes down to, like, if you had a bell curve, an actual bona fide bell curve, where the mean, of course, happens, it's right in the middle, right? It turns out that this range here, where you're trying to find 95% confidence level, that the width of this, and I'll put it down here, for a bell curve, this width is almost exactly, it's not, but almost exactly 4 standard deviations. And so what does that mean? It means that you go 1, 2 standard deviations this way, or 1, 2 standard deviations this way. So over here, this would be the mean take away 2 standard deviations. This would be the mean add 2 standard deviations. Remember this? It's the old x plus or minus 2 sigma thing. In other words, 95% of your data is going to come out between x minus 2 sigma on the low side, put an x there to stand for your result, and an x plus 2 sigma on the high side. And it's nice to put this little 95% in parentheses to say exactly what we mean. We have a 95% confidence level that the next random value to come up is going to be between plus or minus 2 sigma of the mean. We've used this a lot already. So let's just putting some words to it. The 2 sigma rule of thumb. Dun, dun, dun. It talks about a 95% confidence level. Dun, dun, dun. It talks about a 0.05 significance level. Dun, dun, dun. Okay, so there's all these dun-duns. All right, example time. Biff's, example 1. Biff's unfair coin. It doesn't come up heads 50% of the time. It only comes up heads 30% of the time. He had to use some sandpaper, I think, to get that to work. But anyway, Biff's unfair coin comes up heads 30% of the time. Cool. Before we do the questions, A and B, what kind of distribution is that? Can you tell me? Pardon me. That would be a binomial. Whoops. Come on, pen. Come on, pen. That would be a binomial distribution. Remember, it's Bernoulli trials. It's the old, hey, I'm going to repeat something over and over. In this case, I'm going to flip a coin over and over. The probability of success is going to be the same every time, 30% every time. And, you know, that kind of stuff. Fixed number of trials, whatever you want to say. So remember that for the binomial distribution, we can figure out what the expected value or the mean, the average value. How many heads do we expect, for goodness sakes? We expect, well, the formula says n times p. So that means 500 coins, 30% of them should come out heads. Really, you're finding 30% of 500, and you're getting 150. And then remember, there was a formula for the standard deviation, square root of NPQ. So that'd be the square root of, put the 500 back, put the 0.3 back, but the Q is always 1 minus P. So if it's 0.3 for the P, it's 0.7 for the Q. And I worked that out, and I got like a 10.25. And so if you want to talk about mu plus or minus 2 sigma, then you would get 150 minus 2 times 10 1/4 comes out to about 129.5 or so to 1 decimal place. And on the high side, 150 plus 2 times 10.25, about 170.5. And then I like to put the 95% here as an indicator of what I'm talking about. That's what we would expect. That's the answer to part A. How many heads would we expect with 95% confidence? With 95% confidence, we expect, you might say 130 to 170 or something like that. Maybe round towards the middle. Okay, cool. Now part B, we might be surprised, it says. Yep, come on. We might be surprised. We might get an extreme result. What number of heads would be considered statistically significant at the 0.05 level? Well, these are different words and phrasings, but it's kind of the same question because 95% confidence is kind of the same situation as a 0.05 level. The difference is how we answer the question, I guess. We would say, let's put this in another color. We would say, well, we expect 129.5 on the low side, so maybe say 0 to 129. I'll kind of round out. Higher than this, so maybe 171 to, what's the most we could get? 500 heads would be statistically significant at 0.05 level. So if the guy only got like 125 heads, you'd say, oh my gosh, what is that? Or if the guy gets 180, you'd go, oh my gosh, that's surprising. Surprising. I'm so surprised. Okay. Example 2. In the past 70 years, 2,052 tornadoes have been reported in Minnesota. Thus saith the Google. Must be true. We'll take it as true. 70 years, 2,052 tornadoes. Okay. So in the next 5 years, how many we expect with 95% confidence? We might be surprised. You see, this is the same kind of question. But is it the same kind of distribution? Is this a binomial distribution? No, it's a Poisson. Remember that one? I think that was 2 lectures ago. This is a Poisson distribution. Random arrival process, right? That's what it's called. You expect a certain number every period, but really there's no limit to how many might show up and all this kind of stuff. They're all independent, blah, 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 all these rules. But anyway, for a Poisson distribution, the mean is, well, you have to kind of solve it like this. They said that there's 2,052 tornadoes every 70 years. What we got to figure out is how many we're going to get in the next 5 years, because that's our period of interest. So the mu stands for how many do you expect in the next 5 years. So you solve for it. 2052 in 70 years means how many in 5 years? And if you do the cross products and all that, I came up with 146.6 would be expected in 5 years. That sounds like a lot, but I guess it's a pretty big state. And then for Poisson distribution, remember the standard deviation is simply this, the square root of the mean. And if you do that, you'll get just about 12.1. So if you do the plus or minus 2 sigma rule of thumb here, you end up getting 122.4 up to about 168.8, and that would be your 95% confidence level that the number of tornadoes in the next 5 years in Minnesota will be somewhere between, maybe 123 and 168, something like that. That's part A. Whoops. And then for part B, we might be surprised. So how many would be considered surprising? Now again, 0.05 level is talking about the same boundaries or borders or whatever you want to call it as a 95% confidence level. So we can just look at these numbers and say anywhere between 0 and 122, I'm rounding outwards, so to speak, or anywhere between 169 to infinity, I guess, would be considered statistically significant at the 0.05 level. By the way, you could use different significance levels and then your range would change. You know, if you wanted to be 99% confident, your interval would have to get bigger to make sure you catch it, because you want to be 99% sure that you catch it, so to speak, which would be a 0.01 level. Okay, Acme light bulbs have an average life expectancy of 900 hours, and they give you the standard deviation. So we don't even have to figure it out. They told us. So this is like somebody working on the QC technician on the assembly line tests the light bulbs and comes up with these statistics. Okay, so we're going to select one of these bulbs at random. What life expectancy do we expect with 95% confidence? Well, with 95% confidence, we expect mu plus or minus 2 sigma. So you take the 900, that's the mu, minus 2 times 12, and you'll get 876 hours on the low side. And on the high side, you'd take 900 and you would add 2 times 12, and you would get 924 hours on the high side. And this would be your 95% confidence level estimate, whatever you want to call it. Interval, that's what it is, an interval. That's the answer to part A. You might be surprised. At a 0.05 significance level, anything under 876 or anything over 924 is statistically significant at 0.05 level. So I hope this is starting to really kind of, that's an 876, not an 8%. Come on, you. 876, there we go. Okay, so I hope you're kind of catching on to the pattern here. So confidence levels, statistical levels, even p-values, they're all kind of talking about the same thing, but maybe coming at it from a semi-different angle or something like that. Okay, so we're almost done with the lecture, but before we end, let's make sure we're using our language carefully. You got to be very careful with this word significance. And here's my favorite example in the whole world, and this is a real, honest to goodness, taken from the real newsreels out there example. This statement was, I think it was in an ad, I forget. It might have been an ad, it might have been an article in some health magazine, I don't know what it was, but it came from somewhere. It says, people on the Atkins diet, I think that's the one where you eat meat. People on the Atkins diet were followed for 1 year, and they were indeed found to have a significant weight loss. Woo! Dun, 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 dun. Celebrate, sell the stuff. We're going to sell a lot because significant weight loss, that sells. That sells, right? Significant weight loss. Okay, they're using the word significant. That's what they're saying. Significant. You know what that means. It means wow. Doesn't significant mean wow? That's the way it's used in any commercial anywhere. Significant. Wow. Okay, I make my point. What does it mean, really? What does it really mean? Okay, well, think back to all the examples we've been doing when we said 0.05 significance and all this other stuff. What did we mean? We meant less than 5% likely, right? And an article like this, you can pretty much guarantee that they're using a 0.05 significance level. They're using 95% confidence. So what it means is something like it's less than 5% likely, should we put it that way? Less than a 5% chance, something like that, that the amount of weight loss, because that's what we're talking about, is how much weight loss, that the amount of weight loss was due to dumb luck. They're saying, wow, they lost weight, and I don't think that's a dumb luck result either. That's not a dumb luck result. That's statistically significant. You wouldn't expect that to happen by dumb luck. They lost that much weight. Okay. Now ask yourself this. Pick 100 random Americans and follow them for a year and see how much weight they lose, right? How much weight do you expect them to lose? 100 Americans. Follow them for a year. Do you expect that your Americans are suddenly going to be 20 pounds lighter? No, not if you're picking them at random, right? And to be statistically significant, it would have to be like, you know, it's a surprising result. That's outside the realms of chance here, right? Well, what's outside the realms of chance? Turns out you don't have to lose much weight for it to be outside the realms of chance. So what it does not mean is that they lost much weight at all. It does not mean that they lost much weight at all. It would not take much weight loss to say that that was not a chance result, or that it was less than 5% likely that it was a chance result. Turns out it was only 4 pounds. These people lost 4 pounds. Now, you could say, well, 4 pounds, you know, that's something. It's like, yeah, but it was a year. You're going to follow a diet, a strict diet for a year and lose 4 pounds? Is that worth it? So it's not practically significant, I don't think. I wouldn't go, oh, wow, I'm going to get on that diet right now. It's like, no, a year to lose 4 pounds, a year of meat, maybe some broccoli or something, I don't know. And all you lose is 4 pounds. I can lose 4 pounds in a week if I just don't eat. That'd be easy. Just drink water. Boom, done. I don't like to do that, but, you know, you could. So anyway, yeah. So try to remember, statistical significance does not mean wow. It just means not easily explainable by chance, you know, something like that. Besides, you can't prove anything with statistics. Haven't I said that earlier? Statistics never proves anything. It's all about chance happenings. Chance never proves anything, right? Just because lightning struck doesn't mean lightning couldn't have struck. It doesn't prove anything. Okay, well, I hope you kind of enjoyed that one. Now we're going to get into... Oh, I forget. I'll just stop.